guys have seen. So this homework, we need to implement a DBScan algorithm, like on some toy database. You can generate some toy database from the sklearn database query, and then it can make sure you are running on a right check.
You make this bigger a little bit, the text.
Okay.
So everybody remembers DBScan, the one with the core points, border points, and noise points, and it's like a paint can. You put in, then you go as much as possible. Epsilon determines this gap of how far away you go to get another core point.
Yeah. So to evaluate the DBScan, otherwise you are not implement the DBScan or other kind of algorithm, or just maybe like the wrong answers. You need to make sure you are on a right track. Then you need to evaluate data set, and the data set you can generate it by the make circle or noise moon, or like the most naive way, the make blobs, which the data set is shaped like this. If we use like k-means algorithm or other algorithm, we will just divide it into some other ways instead of like separate them very good in a good shape like this. If you can run the data set in and label them in this way, means you are in a good track. The implement is pretty straightforward. So basically, as we all know, the DBScan needs us to set the hyperparameter like epsilons and mean points. So we need to keep track of the labels and go through every point in the data set. And to save some computation, I recommend you guys to just pre-calculating the distance matrix, like the cosine distance matrix or the Euclidean distance matrix, and store it on some data structure. Then you can just recheck whether the point is a core point or access point or other noise point. And then you just need to go through the matrix one by one to check how many of the neighbors in the epsilons, and are they, and to determine the point is a core point or not. For some reason, if you just like to do some naive approach by use for loop to iterate the points in the matrix, maybe you will find some weird behavior in Python for loop when because you need to iterate and then to mutate the list of the how to say, like the potential points. And if you are keeping iterating and update your list, maybe you will not update all of your points. So I recommend you guys to implement by while loop and by the index check, and then you will be fine. So after all, I will run my code here.
So I think he's saying that there are two parts of this. One part is I think grouping those points, right, into creating the neighborhoods and all that. And the other part is running the actual DBScan algorithm based on the structure you create. So it's a two-phase process. In fact, part of the homework is going to be just to run the second part. In the part A, introductory, you're going to have an exercise that says, we already created the neighborhoods for you from some data set, doesn't matter which one, and you only have to implement the second part.
Yeah, exactly.
Right? But when we did both here for the storage data set, which is create the neighborhoods and then run the DBScan algorithm. I think that's what it's about.
Yeah, it's like the whole algorithm build from scratch. And see if we change this to, not everything should go well. So this is the implement DBScan, like my DBScan, and if we change it to takes time. It will go to another myth. So otherwise, if you are running your algorithm, then the algorithm didn't divide the circles, like inner circle and the outer circle, means some part of your algorithm goes wrong, and you need to debug it. Make sure like your output and when your hyperparameter is matched in the sklen, and your output should exactly like sklen, and then means everything goes well. I guess I should run something on the. See, this is my output with the epsilon and the mean points, which it should be same as the output from sklen. Similarly, as the naive probe and the Moon's dataset, both of them are toy dataset, and you should like divide them pretty well by DBScan. I guess that's all.
So now let's talk a little bit about this. I think it's obvious why this works, right? In fact, not only obvious, but it's obvious why k-means wouldn't work here. We talked about this in class. Now, of course, the problem with the DBScan, like we already said, is that data sets don't look like that. This is way too nice. It's way too tight together for the class and too bigger gaps in between. So what he doesn't want to tell you is that he tried to run this on 20 news groups, right? That was a disaster as of now.
Yeah, it just doesn't make sense. The output is, most of them are noise, or most of them will cluster into one cluster.
So he's a little afraid. He is like, okay, I'm coming to class. I'm not experienced. I talk in front of the students. How can I show them I made a mess out of it? Okay, I'm not afraid. I've been doing this for many, many years, 10, 12 years. So we made a mess out of 20 news groups with this. By the way, that's what's going to happen all the time. If problems would look like this, you wouldn't get a job. Right? So problems don't look like this. So you're going to have to run DBScan on a data set like 20 news groups. And you're going to have to explain to us what's going on. Why is it a mess? But before we get there, okay, and I'm sure you're gonna go back and forth with him a lot, you know. But by Thursday or so, he's gonna have a better idea what's going on. Why things would fail? So suppose I don't have this nice data set. Suppose I have 20 news groups, which is a pain. There's a lot of noise in there, and we imagine those are the classes, right? Business versus sports, and there's some other ones. Why would it fail on 20 news groups?
Because there would be points between the two.
The points between the gaps that allow the paint can to traverse, right? So as a matter of data exploration, pedagogy only, so for the class, I'm not saying do that in real life, you know. My purpose is not just to run DBScan and get some result. My purpose is to also understand, you guys to understand what's going on in the data. So we're gonna run an experiment. We don't have it today in class, but we're gonna have an experiment that says, we're gonna cheat. Suppose I'm looking at it from Wen Wei's point of view, not from your point of view, which is a data scientist. He's saying, how can I make it work on 20 news groups? My plan is not, I'm a cheater in the sense that I know the classes, I know what documents on 20 news groups are sports and economic and business, right? So the problem, like she's saying, might be that some document sits right here, and that document is part of the yellow class, but it's too close to the brown class, right? If I'm a cheater, like have God's abilities, can I take off that point? Which is eliminated from the data set. Says, this guy bothers me, I'm gonna take it out. How would I do that? Suppose I'm allowed to do that. I see the labels. How would you identify a point that's kind of in between that says, okay, this point here, it's yellow, and I need to color it yellow, but it's too close to the brown. That's why I make a mess out of it. So suppose I want to kind of curate the data. I want to get rid of these points that are annoying. I have access to their labels. Okay, this would be an extra credit exercise. Can you, okay, 20 newsgroup doesn't work. Can you figure out how to eliminate the points in the gaps, assuming you have access to labels, so that when you run again 20 newsgroups, after you take those points out, you get a nice output? That, by the way, happens a lot in data mining. It's part of the exploration, data digging, so to speak. When stuff doesn't work, how do you go by into it and figure out why it doesn't work? That's not the whole thing. Identifying these points that are troublemakers are not enough, because this is not a practical solution, but it's definitely the first thing you want to do. You want to know, okay, where it didn't work, what are the documents or images, or why it didn't work first. And then you have to figure out a solution that works in production. Okay, it didn't work because of the following reason. How do I get around that? But at least can we try to identify what's going on? So, there was a question?
No. Can we pick up only those points which are extremely different than each other? Like pick only articles which are related to
Right,
arts
so once
and
you know what
politics?
points you want to take out, the question is, can you take them out without looking at the labels, right? Because labels are not allowed in unsupervised learning. And that's much harder to figure out, hey, this is an outlier, it's a yellow point, but it's really in the brown group here. If you have the labels, you could tell that very easily. Also, so that's one part, that I may have some points that are between the gaps. What's the other problem that may happen in a data set difficult like 20 newsgroups? Yes. In the back, yeah. Brown tissue. With a coffee cup? Yeah.
So like you cannot just remove text data once, right? Because you know, so it's a used data set. It's a collection. You have a lot of semantic information, right? So you have each dimension the point is represented. To monitor in a vector space one, you cannot just remove it just because it's a.
But I'm not removing it. I'm not removing the column, the word. I'm removing the document. So I'm saying I pick some troublemaker documents, the ones that would be allow me the paint can to traverse, and I'm taking them out. That's not for the purpose of creating again a production solution. That's for the purpose for me to understand what are the troublemaker points. I think we can do this as part of an exploration, as long as we declare cheating in advance. People do that. They say, now we're cheating. We're going to look with different eyes at the data just to see what's going on.
So, I have a question. So, how do you visualize this like 20 newsgroup which has so many dimensions?
Right, you can visualize it this way. So you got to figure out, take out that point. So you have cheating abilities, you see the labels, and you can take it out literally, but you can't do it in 2D. Right? So how do you figure that out? But I think you should go by DBScan, right? Every time the paint can tries to go where it's not supposed to, take it out, right? Every time. I think first of all you have to play with this epsilon to figure out what epsilon you need. An epsilon too small doesn't advance the paint can. Epsilon tells you how much the paint can go through, right? To what distance it's allowed to find the next core point. So an epsilon that's too small, it doesn't advance even in the dense points. An epsilon too big advances way too much. So we got to play with epsilon first, but even then there will be these noisy points in between that has to be taken out. So I would imagine that I go with a paint can, and every time I say this is the next point I would go to normally, but it's the wrong class, I would take that point out, sort of thing.
How would you know the right value for epsilon? Like you say you play with that.
I think for now we'll just do trial and error. We're not very smart, so let's just binary search, okay? So we're not trying brute force grid. We say he has here 0.18. If I want to try half, I try 0.09, right? That's too small. I try, in between 0.14. Binary search is quite fast to find an
But
epsilon.
then let's say you find the right value. How do you know that it is right? Since you
In 20 news groups or other data sets, they will never look like this nice. So no matter what epsilon I have, the performance of DBScan will be quite bad. But once I start taking points out, my intuition is that things are going to start working if I take a lot of them out.
When you say cheating, like are we like we know the labels already, so are we like allowed to run other algorithms and then come
Sure, you can try that. That'd be interesting. Instead of going by DBScan and figure out what points are the troublemakers, go by not the mixture. Mixture is too globalized.
To know you get the likelihood of each group, right? So
I don't think the mixtures are the right model, but you can try a different model. Some sort of, I would say something very discriminative, like support vector machines or something like that. And then whatever was a long life margin, like outlier, take it out. You don't have to learn support vector machines. You can just call a package. But I would use a very discriminative classifier, like a decision tree, to detect these outliers. But I'm not asking you to do that. I'm only asking as extra credit, try to figure out what points can I take out to see an improvement in DBScan. But I want to go back to my first question. What's the other problem? So one problem is points in the gaps. What's the other problem?
We don't have any shape. It's all random.
Shapes are good. DBScan doesn't need shape assumption.
No,
Any shape you have, it's fine.
Cluster. I mean, the points are not gathered in a cluster. They're all scattered.
Oh, she wants to say something interesting, but yes.
It's a low density,
There's a
data.
gap in here,
Yeah,
right?
so-
In one class, so one problem is between the classes, there's some noise points. The other problem is inside one class, there's a big gap. Remember, I'm a cheater, right? So what can I do with the big gap?
Add more points.
Can I add some fake points? That'd be extreme cheating. To say, okay, well, the problem is there's a big gap here. I don't have those documents. It's empty. I could increase epsilon to try to jump over the gap, but that will create an epsilon so big that jumps way too high in different directions. Maybe that's no good. Another option would be to start adding points. If I am that much of a cheater, I would probably add images or documents that make no sense, right? Because I would go by the feature matrix. I say I want to add a point right here. Right here means an average of the points around, right? So I would go, here's a big gap. There's nothing in between. Make an average of the points around the gap, like literally the arithmetic average. That value is like exactly in the middle of the gap, right? Now that won't be an actual document or an actual image. It will be some vector, numerical vector that has 700 or 100,000 attributes, whatever. And that doesn't correspond to a real document. But still, I think it's okay to do that as part of the data digging to see how big the gap is here. You have a question?
But how will you differentiate between two gaps if you don't have labels? So which is a gap I want to add a point?
No, I have labels.
How do you have it?
So I'm cheating big time with labels. I can find out gaps even without label. By doing data density estimation, I can tell when there is a gap in the data. But what I specifically want for DBScan is a gap that's inside one class. If I don't have the class labels, I'll see gaps, and they wouldn't bother me if they're between the classes. The thing is why I need to cheat. The reason I need the labels is to determine if there's a gap inside the class, because that would be a problem. So, options for the gaps inside the class, add points, would be fake points. Increase epsilon, although that is a very dangerous thing to do it way too big, because you don't want to jump over the big gaps. What else can I do?
Repeat points, like
So a more reasonable solution for this sparsity problem, where the classes are not really clustered together well. In the DBScan sense, together means it's kind of a density contiguous thing. In terms of k-means, cluster well means they form a ball. In any cluster algorithm, when classes are, one class is separated, suppose this brown class is really two parts, that part and that part. I can ask for more clusters. So in 20 newsgroups, there's 20 classes. In the MNIST data set, there's 10 classes. I could say I want a k equal 50 instead of 20 or 10. Now what that's going to do is going to create a class that's all the brown in this way, and another class that's all the brown that way, if there's a separation between them. And then I have to figure out at some point, okay, the following three clusters, they all actually the same class. This is not just DBScan. Even in k-means, if I start with a big K, I create a lot of clusters. At some point later on, there's a pruning phase that says, maybe I can join those three clusters together by some mechanism. If their centroids are too close in K-mean, I can decide to group them together. I'll have to find a mechanism like that here. Even though I determine that the Brown class is really this and that, the three classes, maybe there's a mechanism that will allow me to put it back together. That's actually not a bad strategy, to start with a large K. In the case of DBScan, large K corresponds to what? So large K is for K-means. For here, how do I get more colors? Small epsilon, right? I start with a small epsilon, and I get 100 classes. I know it's only 20 classes, but I'm getting 100. That's okay, as long as I don't have, each one of my clusters is consistent, is part of one class. Maybe then I can start joining them.
Would this approach be kind of a mixture of whatever you do for the DBScan or K-means and then applying hierarchical clustering to some
I guess you can combine things. That's not my intention for the homework. My intention is to take on DBScan and do whatever we can to understand why 20 newsgroups is not an appropriate data set for DBScan. In fact, I know already that no real data set is that appropriate in here. But we'll play with, maybe there'll be 20 newsgroups and another one, and I want you guys to dig into the DBScan and see what's going on with it. Okay? Thank you, Wenwei. I think soon we'll know more about it. This homework is probably going to be posted today.
Right.
Yeah. Yeah, we could. You can shut down. Okay, so now we need to move on. So you're going to get a homework that's more clustering, and there's a lot of back and forth with DBScan and hierarchical clustering. That's clustering part B. But now I'm moving on to a new chapter, which is dimensionality reduction. PCA. Everybody heard of PCA, right? How many people heard of PCA? How many people know what P and C and A stand for? Hands up. What's the C standing for? Component. All right. And how many people know what those components are in English? Like, okay, what are they? What PCA comes up with components, which are what? Right, there's some new representation of the data. Instead of 700 features, now I have it in 10 features or 15. But PCA has a very specific goal for what those features are. It's not just 15 features picked at random. It has, what are those features? Anybody knows that? What's the objective of PCA? When I say, give me 3 features of the data, I plug in those images, I say, I'm asking for 3 features.
Find the smallest eigenvalues.
That's what it comes down to, the biggest eigenvalues. It comes down mathematically, but what's the goal? High? He remembers something.
Not exactly.
High variance, right? So I want to do, the PCA will be 2 lectures, today and Wednesday, and I want to do a little bit of introduction and common sense first. But not just common sense, there will be math, and then next week we'll do more derivations of PCA. Remember when I told you that that mathy lecture was like the most math we ever had? Like it was 2 weeks ago? Yeah. I lied. So before we do that, I thought I'll take 10 minutes to talk about Lagrangian multipliers. Or constraint. Now this is pure mathematics here, but I won't do a very mathy class. I rather want to explain the intuition behind it. I don't expect you guys to remember any of this math. I'm not going to ask you for it, exam or homeworks. But I want you to know What's the intuition between Lagrangian multipliers? Because you're gonna hit this. This and the Newton, what's called? The finding the root with the Newton method. You gotta know those two things. Now the exact equations, you can look them up online. You don't need to remember the exact equations, but the principle you're gonna need to know. So first of all, constraint optimization looks like something like this. Objective, maximize, I don't know, x squared plus y squared. That's a f of xy. Right? Subject to, that's the constraint. So x and y here in this example are real values. Of course, without a constraint, the objective is plus infinity, right? I want you, first of all, to start thinking about objectives differently. So far, I think probably the last math you did was somewhere in college or high school, this kind of math. You look at this and say, I can easily drive it to plus infinity, all right? Because I can make x very big or y very big is unbounded, right? Instead of thinking like that, I would like you to think of not where the objective goes, but what kind of values have the same objectives. So I wanna kind of think in a different way. I want to have all the pairs x values. So with the property that f of xy is a constant. So I want to think of objectives like what are the pairs xy that give me the same objective value. Now this is very easy. What is this geometrically? A circle, right? X squared plus y squared equal a constant. It's a circle. So how does it look? This has objective, say, 1. This is the circle that corresponds to x squared plus y squared equal 1, right? And now I have a different one that corresponds to a different objective. This is the objective that says x squared plus y squared equal 3, maybe. And then there is a different circle that says x squared plus y squared equal 5. So I could have maximize or minimize. In this case, this is called a contour plot. Typically, they use different colors here. The minimum is in 0, 0, right? And the more I go further from the minimum, this is a convex function that just goes up everywhere. Right? But I can have a more complicated function that goes up and down. So I would like you to think of objectives, not like how do I make it to plus infinity, but rather that at contour plots that says the minimum is in here, and this is all the x and y's that gives me a 1. This is all the xy pairs that gives me 3, and so on and so forth. Now, of course, for every line in between, there will be 1 here. That will be x squared plus y squared equal a 2, right? So this is really a surface that has these contour lines. A contour line is all the points that have the same objective. In this case, those are all circles. Right? We all good with that? So if we're to plot this, it will look like a parabola in 2D, right? With the minimum and then all the sides going up. Now suppose I want to add a constraint to it. If I want to minimize this, the minimum is going to be here. The maximum is going to be any side goes to plus infinity. Now suppose I want a subject to x plus y, say bigger than 7. So this is a 2D plot, contour plot, right? Now, where is x plus y bigger than 7? What is this? This particular constraint is a line, right? because it's a linear constraint. So how does that look? I think that's something like, say, x plus 2y, make it more interesting. So x plus 2y equals 7 will be when x is, for example, 1, y has to be 3, right? Kind of like here. And then x is 7 all the way here. So y has to be 0. So when x is 7, y 0. So I think this line, this constraint line, I don't know if I do it right. Something like this. You guys can draw letter 1. So that when x is 1, y has to be 3, right? 1 plus 6 equals 7. And when x is 7, y has to be. So that's nice. It's a linear constraint. And geometrically, when I say x plus 2y bigger than 7, I mean what? I'm looking for x and y on what side of this line? Upper. So this side here is x plus 2y is bigger than 7. And this side here is x plus 2y smaller than 7. And the line itself is x plus 2y exactly equal to 7. So now I'm going back to my problem. If I want to maximize subject to this constraint, I can't go on this side, right? Because this side is forbidden. Usually the constraints, so the objectives determine how well you do in machine learning, data science. Not everybody can reach an actual optimum. Actual optimums are really difficult because the functions are not nice. So you cannot optimize a function unless you use brute force. Any EM or any sort of other algorithm will get stuck. So how well you do, it's an intense field of study with all kinds of fancy mathematical techniques. But constraints are usually set in stone. You are not allowed to break the constraints. So what we're saying here, we don't want this side, the small side. We want the big side. Right? So I think I can just get onto this side, the contours. If I keep going in that direction, I'm going to be in the valid side. And I can go to plus infinity still, right? Because this parabola is centered here. It goes up on all sides. Therefore, if I could keep going that side, I get to plus infinity, right? Okay? So if I want to maximize this, so if I maximize, I still get to plus infinity because I go on the side that's allowed. What if I want to minimize? The minimum without constraint is in 0, 0, right? Yes. But 0, 0 is clearly not allowed here. It's not in the region that's valid. So that's a question, the interesting question. Now I want to minimize this function, but I have to stick to that side. Okay, I can't. See, the way the parabola goes, it goes up, it goes down to the minimum. At some point then, if I go my objective is to go down to the minimum, but the more I go to the minimum, I may be forced to be only in one side, and that's not allowed. The side is not allowed. So I somehow have to stick at that. I have to imagine this as a wall, and I can go down on the wall, but I can't pass the wall. So that's the kind of problem the Lagrangian multipliers are solving. They're saying you want to minimize the function with this one. Normally you take the derivative and set it up to 0, right? And then you think that's the minimum. And it will, right? If we differentiate this function, the minimum is going to be at x and y equals 0, right? But how do we stop at this line? That's the subject. That's the constraint, right? So let's do this as an intuition. So the intuition is Lagrangian multipliers. The intuition is that at solution, the two curves are, one is the objective, the other one is the constraint, right, are tangent to each other. So there's a bunch of mathematical properties that you need to satisfy. We'll ignore all that because we're not in a math class. But the intuition is, at some point, see those contours? Some of these contours, I'm trying to get to the center here because I'm minimizing. Some of these contours will be too small because they're not touching that wall. Those are no good because they're invalid. Everything on a small contour is just simply breaking the constraint. Everything on a large contour, I'm probably going too far. I'm satisfying the constraint, but I'm not minimizing enough. So the moment when I'm going to minimize it is this contour, the one I need. That contour is the one that's going to touch my constraint line, right? So the reason they are tangent is because if the contour that I'm looking for is too small, it means there is a better one that's a little larger, right? No, sorry, if it's too small, what's the problem? It's invalid, right? The constraint is broken. If it's too big,
It's not the minimum.
it's not the minimum, so I could go down. So the intuition here is that the solution is going to happen when the contour that I'm looking for is tangent to the constraint. Tangent meaning just touches once. A little bit too big, then it's not minimum. A little bit too small, the constraint is violated. How many people with me? Okay. How many people have seen this before? Okay. So this is something that you should know how it comes. So there's this magic tangent here, which means the two differentials are proportional, because differential is a tangent to the curve, right? And then the two differential must be proportional. So how do we translate that into math? Okay, we say take the Lagrangian, which is the objective, minus, this is called Lagrangian multiplier. There's a number, lambda. That's the proportion between the differentials. Times the constraint. Constraint was x plus 2y minus 7. So what did we do? We say, this is my objective. That's my constraint. By the way, this also means that either the constraint, it's irrelevant, as in I can still maximize it, like I don't have to pay attention to the constraint at all. Or if it happens, what does it mean? How is the constraint going to be satisfied? At the solution, this is bigger or equal to 7. It's saying you can take all the right side. But in reality, the solution will be exactly equal to 7. So in optimization, there's two kinds of constraints. Inactive constraints that do nothing. You can take them out. They don't affect your solution. Right? Like if I say here, x plus 2y has to be smaller than 7, the other constraint. That won't affect my solution because my solution without the constraint happened to satisfy that constraint, so I'm good. So the constraints are two kinds, either inactive, you can take them out, or they active and the solution is tight. Tight means equality. So that's the case in here. The solution you see, just by the geometry of the space, you know that the solution is going to happen exactly on the constraint line. So that's going to be equal 7. That's why I can set it directly equal 0 here, because I know the solution is going to happen on the constraint. Right? So this is an active constraint. So I know it will be satisfying to the equality. Now if I take the differential of this thing with respect to x, what do I get? Two x minus lambda x equals 0, right? I do it just like I do the differentials. I set up the equation to 0. So I get here lambda equal to minus lambda. Sorry, I'm not that. That's 0, so that means x equals lambda by 2. I'm not that fluent into this. How about if I take the differential of this with respect to y? 2y minus 2 lambda equals 0. So y must be lambda. And if I take the differential with respect, so this is the optimization part. If I take the differential with respect to lambda, because of the form, what's going to happen? My Lagrangian contains lambda times the constraint. So if I take the differential, I'm going to get the constraint, right? Which is x plus 2y equal minus 7 equals 0. Which is just enforcing the constraint. This differential, what it does, it says enforce the constraint. So enforce constraint. So now, of course, I can solve this whole thing because I can do substitution. I can plug x equal and y equal into there. With that, is that going to work? How much is x? Lambda by 2, that's x, plus 2y is what? 2 lambda equal 7, right? You guys follow me? So what am I going to get? Multiply by 2 here. Is it 5 lambda equal 14? I haven't done this before, so I just made it up right here in class. I hope it's not a mistake here. Lambda equal 14 by 5. So now I've got myself an x and y, because x is going to be 7 by 5, and y is going to be 14 by 5. You guys can check if this was the correct calculation. So what were the steps here? The important step that I want you to remember is the intuition of Lagrangian multipliers. The two differentials, if there's an active constraint, they're tangent to each other, so there's a proportion, lambda, between them. We don't know what it is, but we know it's a proportion between them. So we set up this Lagrangian function, and then we differentiate it like before, like without constraint, we differentiate it in x and y, right? That's how you set this to 0. But now we have we have this constraint, and we differentiate with respect to lambda, we get the constraint. And so we can solve this system, and we get x and y. Yes?
I don't understand why there should be a proportion in between them. What exactly do you say there's a proportion in between them?
Because the differentials in here have to be the same geometric orientation, right? If there's two tangents, the differential in there, they're the same tangent, right? So that translates, because of differentiation, into a proportion, I guess, between the functions. If they have the same differential, they have to have a proportion between the functions, no? I think everybody understands the fact that the tangent, the differential in this point, both for the objective and the constraint, is the thing in between. Now, this happens to be a line, but this could have been any constraint, right? I use a line because it's easy, but I could have had some other quadratic form or something. And then the other stuff is if the tangents, the differentials are the same direction, right? Why is it that translates into when I set up the them equal to zero, I have a proportional constant between them. I think the intuition is easy to follow if somebody shows it to you, like now, but then you have to go through a bunch of calculations. All right. So I thought it would take 10 minutes to explain this technique, what's about. It's not like you're going to remember the calculations, but you have to remember the idea. So now, let's talk about PCA. So the other thing that we're going to need, that we've already done it, is the covariance matrix. I'm going to take some of this out here. Maybe start the PCA here. So here are my data points. Xi is xi1, xi2, xid, say, right? And this is I equal 1 to n. I have n data points. So the purpose I have is to replace every xi with some other, say, xi hat that is not those d numbers, but some other k numbers. So this is xi1 hat, xi2 hat. Those are different numbers, xik hat. Right? So from d dimensions, I have now k dimensions. And those are not the same values. Those are different vectors. So I need some sort of objective. I'm going to say I want the sum for all data points of, say, that's not quite mathematically correct. So what I say is, like, I want those points to be as close as possible to the original points, right? So minimize means as close as possible. But how does that play out if this is a d-dimensional vector and that's a k-dimensional vector? So I said k different than d because I want, the whole purpose is here for us, dimensionality reduction. But geometrically, I can't take the difference between vectors if they don't have the same number of dimensions, right? So what we're going to say, we're going to say we want this xi to be in the same space as x. So those are different values, but in the same space as x. So if this is d dimensions, that will be d dimensions, but then we'll impose the conditions on why the data in xi is lower dimension. So this is a point, let's say this belongs in some r to the d, right? This is still a point in r to the d, but with lower dimensionality. We'll have to make sure this as a story is fine, but later on we have to make sure this actually works out correctly. So let me try k equal 0. So I still remember xi here, my xi hat is still in R to the d, right? So I'm still representing my data points in the same space. If I have data that's 50 dimensional or 784 dimensional, I'm going to get a point in those 784 dimensions. But the dimensionality on that data is 0. Now what does 0 means? So what is 1 first of all? K equal 1 means xi, those xi bars are on a line, right? So how do I look at this? I say, okay, this is an R to the D, but really K is much smaller than D. K, it's much, much smaller than D. What does it mean? It means that in 20D or 700D, I can get a bunch of points that are all on actually on the line. I feel like I got you guys stuck with that.
How does it come into projections?
You can think of them as projections, if you want, although that implies a very specific procedure. And here I'm talking generally. I'm saying, what do I mean for this K to be smaller than D? That's a much smaller subspace, right? So K dimensional subspace. So I don't want to make a big deal out of vectorial spaces right now. What I want to say is in 2D, right? Even in 2D, if I have those points, they're not in the plane, they're in 2D, right? This is D equal 2, right? But the reality is that those points live on one line, so K equal 1. In 3D, here's three-dimensional space, right? Those are points, all points will have 3 dimensions in here, but if I look at these following points in this space, the reality is K is equal 1, although each of them has actually 3 coordinates. Right? So my point, my purpose for right now is to live in the same space. So the result, if I use MNIST, the result from PCA will be 784 dimensions in MNIST data space, but it will so happen that the actual dimensionality of the data will be much smaller than 784. So if the data was in here, those are my original data points, right, in 3D. What I'm doing, I'm keeping them the same space, but now I'm mapping them on some sort of line. There'll be a projection, but I don't want to say it has to be a projection. So let's go even further. That's K equal 1, but what's K equal 0? What space has K equal 0? 1 point, right? So this means there's 1 point. Let's call that mu, right? Mu, everybody, every xi will go to xi bar, that's the projection, which is going to be mu. Everybody goes to mu. Which mu is the right mu? Well, I want to minimize this, right? So if I want to minimize the objective, is to say minimize the sum from 1 to n from the original points to mu. What mu is the one that realizes the minimum here? The mean. So mu will be the sum of the xi divided by the total, the count. Right? You guys, I think, have to do this for k-means to prove that for a bunch of points, to realize this minimum, you get the mu. And you can do it with derivatives if you want. It's easy. Right? So that says one thing. If you want to represent the whole data set with 1 point, what point is the best one to represent the data with? That is the average of the data points or the mean. Okay? That was the homework exercise. Okay, now let's see what if I want to use 2 points. A line. So what if I want to use K equal 1? What's that saying is that these are my xi bars, right? We don't know the line, but we know that we want everyone to get on the line. So every xi went to an xi bar, right? Every point has to be mapped to its own. It's tempted to call it projection, but that already assumes I'm going to do 90 degrees angle. This objective doesn't say they have to be geometrically projected. They just have to say, find them for me on a line. So the question is, how do I take my data, it's in d dimensions, and map everyone on a line? There's actually two questions there. Xi bar are on a line. Let's call that line E. E is a vector that gives the, E is the tensor that gives the line direction. So the norm of E is 1. Because as a directional vector, I only have to give the direction. The size of it doesn't matter. Right? So a line, if I say a line, the line is given by the direction. And perhaps by, once I have the direction, there's a shift of where the line is. I can shift it a little bit. Right? So there's two questions. What is the best E? What's the best line to use to put the data on? And once I have E, who is exactly xi bar on E? Like suppose I tell you, this is the line. Now you have to take every point and put it on that line. Well, you can go many places with it on the line. In this case with the mu, I don't have that problem because it's only 1 point. Everybody goes to 1 point exact. But on a line, I have two problems. Where do points go? And what's the best line to use? I could start rotating the lines, I get a different line, right? Who's with me so far? Good. So we have those two problems. Here's how we're going to think. We're going to say every x point, xy bar, is xi on E, that's an English term, which is really mu plus AI times E. So the first thing that we're going to make an observation, we're not going to answer the question what's the baseline E, but we're going to make the following exercise for you guys at home. Mu belongs to that line. It's already on line. So I don't know what's the best line, but I bet that line passes through mu. So again, I compute the center of the data, that's the mu. Suppose the center is somewhere in here, mu. What I'm saying for you guys to prove is that the best line has to pass through mu. If that base line doesn't pass through mu, I can shift the line. Suppose this is the best line. I can take that line down, keep the distance, the angle, keep the direction, move that line down to mu, and now I've got a better representation of the data that will give me a smaller objective. So as an exercise, prove that the best line, which we don't know what it is, has to pass through mu.
So it's simple linear division, right?
Yes.
Sine always passes through the mean because of the objective.
Yes.
So
It's
that's
exactly the same equation like logistic, linear regression. Okay, so we'll assume you guys can do this at home. We'll assume that mu is already on the line, the average of the data. It's a very simple exercise. Now, if the mu is on the line, I want to redo that picture to make it much nicer. here's a line. I have this line here. And mu is on it. That's the average of the data. This is the line E. So a line E is defined by a vector that's unidimensional, right? And it's just the direction of the vector that determines the line. We have these unidimensional vectors that just determine where the line is, right? Any rotation accounts for that. So now I know this is the average, and I know I have to take some point xi, and I know I'm going to map it somewhere to xi bar. That's what we said. We have to figure out the line. We also have to figure out where each point goes on the line. So far, we only figure out that the mean is going to be on the line. In fact, we didn't. You will do it at home. Now, here's what I want to do. I want to think of this xi projection, or I don't want to call it projection because it is the projection, but that's going to come out as a result of what we want to do. I don't want to say it must be a geometrical projection. I want to say this is the mu plus E times AI. So what is this saying? Everybody on this line here is the mean that's already on the line, plus this is E, that's the unit vector that's on the line, and AI is a real number. It's a scalar. So everybody on the line is the mean plus minus some distance on the line, right? If this is E1 and I need to go 14 places, AI would be 14, right? And if this is the other way, that's another point, xj, right? And this is going to get projected here. xj is going to be mean plus E. E is just 1. It only controls the direction of the line times aj. So what this is saying, on a line, every point becomes some going back and forth from the mean. So it's the mean plus how many units I need to go that direction, or how many units I need to go that direction. Those units are a scalar number, are a real value. That's the AI. It multiplies with E. E is 1. It just tells you to go on that line geometrically. And it starts from the mean. So who's the mean? The mean is the mean itself plus E times 0. So the A corresponding to the mean is 0, because the mean goes to the mean. How many follow me so far? Okay. Don't be shy. Yes?
Mean something like the intercept, like y is equal to mx plus c. Is
What?
C the mean? So it's like y is equal to mx plus c. Is c the intercept is the mean?
This mu?
Yeah, mu.
Mu is the mean. We already said that for some mysterious reason that we're going to figure out at home, the mean has to be on that line. If the line somehow doesn't pass through the mean, there's a better line parallel with that one that passes through the mean. I think you already did that if you took a machine learning class. The regression line has to pass through the mean of the data. Okay, but then I don't want to insist on that. That's easy. But then, is it everybody understand here what I'm doing? I take every point and I map it to the line. I don't put any constraint where it has to go. I don't say it has to be a geometrical projection or anything like that. I'm saying every point becomes the mean plus going some units that way or some units the other way. Every point on this line can be represented by the center plus E, which is just the direction of the line, times a real number. Every point on the line can be represented like that. Yes?
For the point J, don't we have to negate the factor E?
No, AJ would be negative.
Oh,
E stays 1. E is only the direction. It's a unit vector that just gives the direction where to go. For this to make sense geometrically, I can't just put AJ, because I can't add a scalar to a vector. But if I put the E here, I'm just saying move on that line so many units in that direction. Or if it's negative, move so many units. If AJ is minus 5, means move 5 units, 5 E's in the other direction. And if this AJ is say plus 3, plus 2 means move 2 units in that direction. So AJ is a scalar that tells you how much to move on the line back and forth from the mean.
Visually, so we have one line. If you change the orientation of the plane, let's say, so a line can be viewed as a point. Is that
A line is not a point.
It can, if you, yeah, it can be viewed as a point. Like,
So this line is true that it's pinpoint in mu.
Yeah.
That's your exercise. But there are many lines that go through mu, right? I still have to find which line is it, right? There are quite a lot of lines that will pass through this point. The fact that it passes through mu is not nailed down. Could be who knows which line. There are many lines rotated in mu, right? Yes.
Is there any formula for this line? Because we understand we are mapping all the points onto this line. But is there any particular formula?
So we need
for
to
this
find
line?
E. Once we find E, that will give us the direction. We already know mu. So imagine geometrically we have a line that passes through mu. The only thing is that it can rotate in mu, right? Bigger chalk. I have this line, and it's pinpointed already in mu, but now it can rotate in mu. So what's going to control this rotation? Who controls the rotation?
a direction.
E. If I found E and I know mu, it has to pass to mu and it has to have that direction. That's going to determine the line.
How do we find E?
Let's see. Yeah, good question.
Is the mean here a one-dimensional real value or n-dimensional?
Mean is the centroid, like in k-means, is the average of data points. Mu is a vector in here of d dimensions.
So mu here is a vector of the
It's the average of all the data points. Same notion as the centroid and k-means. And we know the line has to pass through that point. I mean, we don't know yet, but you guys can prove this at home. It's very easy. Okay, can we move on? No. No, we cannot move on.
So in KV, the notion of a ball, it can be viewed as a circle and then as a point which is a
Okay, I don't know where you want to go with this.
just trying to understand how you are.
So I don't want to think of k-means. I want to think of this. I have a bunch of data points in 3D or 5D or 20D. And I'm looking for a line, E. I know that line will pass through the center of the data. And then I want to map all the points to this line somehow. It's two-stage. I want to map the points to the line, and I want to find the right line. I want to minimize this objective. That's my plan. Because I want the points to be as close as possible to their original positions. I could define this the different way as a regression objective. It will give me the same exact line.
So E is the slope, right?
E is the direction of the line.
So it's not.
E is a vector. This vector E here, you can put it here, it's the same vector. It's a unit 1 vector that its own purpose is to control the direction of the line.
I imagine it as a slope based like.
Imagine it as a vector in d dimensions of size 1. And whatever this vector is, it controls the direction of the line. Okay, I think I can move on now. This is how I'm going to think of these projections or mapping points. Each mapping point, the bar ones, is mu plus some units on the line back or forth. So it's literally E times AI. Okay. So now if I do this, let's see what we're going to get. Split this into what's my objective? Is the sum from I equal 1 to n of xi, that's the original point, minus, now the projections are mu plus EAI, right? Is that square? I missed a square. Square. Of course, we pick the squares because that makes the math and everything goes very nice, just like in regression. This has a nice intuition. If the points are on the line, the distance between x and the point on the line is going to be exactly this segment, right, from x to the line. So why do I want to minimize the squares? That's going to be kind of the errors. The squares are actually actual distances, right? So I want to minimize how well the line is positioned among the points. I'm sure you've seen this plot at regression where it says if I have a bunch of points, the line that passes through the middle of the points minimizes the square distances, is the square loss. Right? So how does this go? I want to minimize this. But keep in mind that at regression, you guys did something with labels there. So the main difference, I don't want to talk about regression right now. When you do regression, you had something with the labels. And now we have no labels in here at all. We only have the data points. If I differentiate this with respect to maybe before we differentiate it, we look at it a little further. Formula here, then we have to figure out where it's coming from. So what happened? Do we know this formula a minus b squared? A squared minus 2ab plus b squared, right? So of course I applied for a sum. So the sum distributed aie squared is this part squared. 2aiet times that. They have to be E transpose so that the dot product works between them to align the dimensions, right? This is a dimensional vector of d dimensions, so this has to be 1d times d1. And this here is the sum of d squares. Okay. So what do we get? Now let's take the differential with respect to AK. AI. What's the differential with respect to AI to this thing? Now this in here is what? E squared is? That's 1. E is a unit vector, it just gives dimension. So if I take the differential, there are many A's in here, but I only pick one of them. What's the differential with respect to AA? 2AI minus 2 E transpose. E has the size 1, but it's a vector, so it's going to multiply with xi minus mu, right? That term has no AA in it. So the sum, where's the sum going? Why there is no sum when I take the differential? Where did the sum go? For each sum, there is only one term that contains the AI. I pick an I here. choose one I. So for that one I, in the sum there is only one term that contains AI. So that I set it up to 0. That's going to be what? AI equal E transpose xi minus mu. That, now we can call them projections. That means xi bar, which is mu plus EAI, right, is the geometrical projection of xi to line E. People know this is a geometrical projection? No? Okay. So how does it look? That's line E. This is xi right here. The question is where is xi hat, which is the mean of the data plus what was it? E times AI. But now we calculated the AI. We figured out what is the AI. So now what is this? Is the mean plus E. Did you do it the right way? I think it's E transpose, I think it's the other way. It's AI times E. I don't think this matters because AI is a scalar. A transpose xi minus mu times E. So I think if you, that's another exercise for you, is to say if this value is exactly that, the difference, this, who's this xi minus mu? This is xi minus mu right here, right? If it's xi minus mu plus the, if to satisfy this equation, this has to be a 90-degree angle. So as an exercise, we want to prove that the vectors, as geometrically speaking, xi transpose, this is now the segment, is perpendicular on line E. So there's a simple calculation that you've seen in trigonometry in high school that says if this segment is exactly that times the E line, that means this segment got to be perpendicular. Now we can call them projections. We knew they're projections, but we don't set the projection as a constraint. We tell it, pick any points on the line you want to minimize that objective. And what did it do? It picked the projections. Good. We still didn't find E though. So far, what this is saying is, if somebody gives you an E to maximize the objective or to minimize the objective, the right points to do the mapping is to project the points to the line. One of you can argue, hey, wait a minute, of course it's the projections. You were taking these distances as the error, right? The error was the sum of distances. So how do I get the smallest distances from, the line is fixed. If the line is fixed, how do I get the smallest? Why don't I project xi here? The smallest distance is the one that's perpendicular to the line, right? So if every point goes to a fixed line, and the error, the objective is the sum of the errors, then every point will be exactly projected. How about E? How do we deal with E? Let's bring back this matrix, which is, this is sigma. So we want to make sure we get the dimensions right here. We want to have a matrix. So this really has to be D times 1 times 1 times D. Otherwise, we don't get the matrix, right? And if we think of this as row vectors, rows are what? 1 times d, right? So this has to be the transpose one. I really want to get the matrix. This is the empirical what? Covariance matrix, right? Meaning if somebody gives you a bunch of points and says, find me the covariance, you do exactly this. So that's approximatively this is the actual covariance matrix. It's n times. Because if you estimate the variance or covariance, you divide by, I think to get the, to get the proper estimate of the covariance, you divide by n minus 1. Is that true? So now let's figure out what this objective is as a function of E. So now we're looking at who's the best E. Let's see. Let's start here. Sum for I of AI squared minus 2 sum from AI squared plus the sum of xi minus j. So what did I get this? I look at this formula, but now I know that AI is this value. So I replace this value here with AI, and I get another 2 AI squares in here, but I leave the other term free, right? Who's with me? Are we stuck? Tired? Yes. So who's got it up to here? We got that. And now what we're doing, once we figure out that's the projections, we have to find E. So I replace ET times this with AI. I get now 2 sum of this. Everything else is the same in the objective. Yes?
So, AX is the summation to the other term.
In this summation, if this is incorrect and missing a term,
So,
why? So you're saying from here to here I'm missing a term, or this one is missing a term?
no, so the AI will vary from I equals to 1 to n.
Yeah. No, this is, I copy the AIs, and I just replace this with AI. I'm assuming I already done this part of the optimization. And then AI times AI, it's AI squared. It's not a tricky thing. I'm missing this square? That's your saying? Fine. Now, where is E in here? So I'm going to say, for the purpose of E, just if I care about E, I want to minimize this in E. Does this term contain E's? That's just data minus the mean. This doesn't contain E. So in here, I'm going to get minus, right? One of these. This is 1 orange minus 2 oranges. It's 1 orange, right? That is sum of E xi minus mu have to figure out where to put a transpose here. Let's move in here. I'm going to say this is even further from I, E transpose xi minus mu times xi minus mu times E. So I kind of open up the parentheses. What I want to go with it is minus E transpose. This is the sigma matrix. This is not a sum. So I don't think we have time to go to all the details, but this is nothing more than a simple calculation. I'm saying this here contains no E. So I can ignore that term. In here I have only minus 1 orange. I open up this parenthesis and I'm getting to be, this is the sigma, is not a sum. This is this matrix here that if you look at it, ET times this times E, it's in fact ET times the matrix times E. The no tricks here is just matrix calculations instead of real numbers calculations. And now we have to optimize this function, right? Now, which is the best E? We have to say, I want to do this, minimize objective in E, which is that. This is the sigma. Subject to what's my constraint? E has to be norm 1, right? E is a unit vector, it just gives direction. It doesn't have scale by itself. So this I can rewrite E transpose times E is 1. That means the same thing. Norm of E, the norm square of E, is E times itself, right? Dot product. So how do I do this? I have a constraint optimization problem. Is the E transpose sigma E minus lambda E transpose E. That's my constraint, minus 1. So now I take the derivative with respect to E. I get what? This is like we did before. We used the analogy from 2D. It's going to be 2 sigma E, because x squared times something, when you take the differential respect to x, is 2x times whatever you had, minus 2 lambda E. That has to be equal 0. So that means sigma E equal with lambda E. Lambda is the Lagrangian multiplier scalar. So that's a value. Remember the lambda from before was, what was it? It was 14 divided by 5. It's a value. So this is the same technique like I've done earlier, that's minimizing some sort of function. It's a quadratic function because sigma is a fixed matrix here. The E is a variable. And subjected to the E has to have norm 1. How many people with me so far? Yeah, okay, let's have a question then.
You made the minus in the...
What?
There was a minus there.
We lost the minus? think we want to maximize. Is that correct? Yeah, I'm looking at my notes. I think you want to maximize this. That's why we get it this way. Okay. For now, we won't remember the Lagrangian details, but I want you to see the analogy that this is just like the first problem we did. Is a optimization with a constraint with the Lagrangian multiplier, and we do the derivative of Lagrangian just like we did in the first problem. Then we got some sort of equation here, right? What we don't know here, what do we know here in this equation? This is empirical covariance matrix. We know this or not? This we know. We don't know E, and we don't know lambda. But anybody remembers this kind of equation for matrices? This is a matrix times a vector, is a scalar times a vector. That means lambda and E has to be an eigen value and vector of matrix sigma. Every matrix that says AX is lambda X means lambda and X are eigenvalue, eigenvalue for that matrix. Geometrically, this says that by multiplying matrix with X, we don't change the direction of X. This is the geometrical definition of an eigenvector. Obviously, when we multiply with lambda, we don't change its direction. Lambda is a scalar, just make it bigger or smaller, or it goes the other way. This is saying by multiplying a matrix with X, typically it changes the direction. Matrices act like rotations. It's very rare for a matrix to multiply, say, same direction as the vector X. Those are very special X's. The X's that the matrix, when you multiply with them, don't change the direction. They're the eigenvectors. So there's quite a few ways to find the eigenvectors. All languages have built-in eigenvectors. What we don't know is what eigenvectors are other than this. I mean, I tell you a nice geometry property of them. Hey, it doesn't change the direction. But then how do we find them? What are they? We have to do this next time. What it's important to know is that I want to put here two things that makes it a lot easier than for general matrices. Sigma has two nice properties. Sigma, the covariance matrix, has two nice properties. It's symmetric. Is that true? Yes. Covariance of adjacent. And is positive semi-definite. That means any vector Z has the property that Z transpose sigma Z is positive. You can try to prove this at home, that if you take a covariance matrix, any vector, real vector, multiplied on both sides with it, will give you a positive value. This is the multiplication 1D, D1, so you get a value at the end. Try this exercise for any covariance matrix. When you multiply with a vector, we get the positive value. Now, those two properties, which are rare, but they're true for covariance matrices, will make the eigenvector, eigenvalue stuff a lot easier than normal. The rest of PCA next time. So we got the most important thing, which is the equation.